Welcome to the lecture on linear programming problem, module 3. In this module, we will consider some special cases which are often encountered while solving linear programming problem by simplex method. Specifically, we will consider degeneracy in linear programming problem, alternative solutions in linear programming problem with unrestricted sign, unbounded solution in linear programming problem, and no feasible solution in linear programming problem. So, let us start with the case of degeneracy in linear programming problem. Let us first define what is degeneracy in LPP. A degenerate solution to an LPP is one in which at least one of the basic variables equals 0. So, degeneracy can occur at the very beginning of the table, that is at the initial stage of simplex iterations, or at some subsequent iteration if there is a tie in the minimum ratio test to determine the leaving variable. At the initial stage, if one or more components of requirement vector be 0, then the corresponding basic variable or variables will also be 0. This indicates the existence of degeneracy at the very beginning of the table. On the other hand, if degeneracy occurs in some subsequent iteration, then there must be a tie in the minimum ratio test. In case of a tie, if we choose arbitrarily one and select the vector as departing vector, then the next solution is bound to be degenerate. To resolve the degeneracy, we can follow the following steps. In first step, pick up the rows for which the minimum non-negative ratio is the same.
Rearrange the columns of the simplex table so that the columns forming the original unit matrix come first in the proper order.
Next, find the minimum of the ratio like this: element of the first column of unit matrix divided by the corresponding element of the key column, and this can be done only for the rows for which minimum ratio was not unique.
If there is no tie in the minimum ratio, the key element will be determined by the intersecting of minimum ratio row and the key column.
If this minimum is also not unique, then we will go to the next step. In step 4, compute the minimum of the ratio like this: element of second column of unit matrix divided by the corresponding element of key column only for those rows for which minimum ratio was tie in step 3. Now, the key element will be determined by the intersecting of minimum ratio row and the key column, again if there is no tie. If this minimum is also not unique, then go on repeating the above procedure till the unique minimum ratio is obtained to resolve the degeneracy. After resolving the tie, use the simplex method as usual to obtain the optimal solution.
Let us consider an example to show how degeneracy in LPP can be resolved by following the algorithm just mentioned. Suppose that we have to maximize z equal to 2x1 plus x2 subject to x1 minus x2 is less than equal to 1, x1 is less than equal to 1, x2 is less than equal to 1, x1, x2 greater than equal to 0. Introducing slack variables x3, x4 and x5, the problem can be written in standard form as shown in this slide. In the first iteration, the vectors a3, a4 and a5 are in the basis and the value of z1 minus c1 is most negative. Hence, a1 is the entering vector. The minimum ratios show that there is a tie in selecting the departing vector. Either a3 or a4 can be chosen as the departing vector. To select the right one, we follow the algorithm and rearrange the columns so that the vectors forming the original unit matrix come first and then the other vectors follow. For this rearrangement, the costs Cj's need to be rearranged accordingly. Now, we find the minimum ratio for the elements of the vectors a3 and a1 considering the first and second rows only, and we find that the minimum ratio lies in the second row. Hence, the vector a4 will be the departing vector. Now, we proceed as usual and do computation for the next two iterations as shown in this slide. The last iteration shows that Zj minus Cj is greater than equal to 0 for all j. Hence, the optimality condition has been satisfied and the optimal solution is x1 equal to 1 and x2 equal to 1, maximum value of z equal to 3.
Next, we come to the special case of LPP having unrestricted variables. Sometimes decision variables are unrestricted in sign, that is, decision variables are positive, negative or 0. In such a case, decision variables can be expressed as a difference between two non-negative variables.
For example, if x1 is unrestricted in sign, then we can write x1 as x1 dashed minus x1 double dashed, where x1 dashed and x1 double dashed are non-negative variables. If x1 dashed is greater than x1 double dashed, then x1 is greater than 0. If x1 dashed is less than x1 double dashed, then x1 is less than 0. If x1 dashed is equal to x1 double dashed, then x1 equal to 0. Thus, when x1 is unrestricted in sign, we can write it as x1 dashed minus x1 double dashed, where x1 dashed and x1 double dashed are non-negative variables. Consider the LPP as shown in this slide. Here x1, x2 are unrestricted variables.
To solve this problem, we introduce three slack variables x3, x4 and x5 and take x1 as the difference of x1 dashed and x1 double dashed and x2 as the difference of x2 dashed and x2 double dashed. Then the problem is converted into the one which is shown in this slide. Here, since x1, x3, x4 and x5 are slack variables, we take the coefficients of these variables as 0 in the objective function.
Following usual simplex algorithm, we obtain results of two successive iterations as shown in this slide.
From the final iteration, we see that Zj minus Cj is greater than equal to 0 for all j, hence the optimality condition has been satisfied here. and the optimal solutions can be obtained as x1 dash equal to 9 by 2, x1 double dash equal to 0, x2 dash equal to 3 by 2 and x2 double dash equal to 0. So, the solution of the origin problem is then x1 equal to 9 by 2, x2 equal to 3 by 2 and maximum value of z equal to 27 by 2. So far, we have discussed the cases of degeneracy in LPP and LPP with unrestricted signs. In case of degeneracy in LPP, we have to be very much careful about selecting the departing vector. If we are unable to resolve the degeneracy, then the situation of cycling will arise and will never reach to the optimal solution. The problem of LPP with unrestricted sign may arise if we solve a system of equation by using simplex method. In that case, of course, we have to introduce some dummy objective function which is to be maximized while using simplex. Let us now discuss the case of alternative optimal solution in LPP. The optimal solution of an LPP may not be unique. If the value of Zj minus Cj is 0 for a non-basic variable, then that non-basic variable can be brought into the basis, resulting no change in the value of the objective function. Thus, the problem has an alternative solution, in fact optimal solution, and in that case we have actually an infinite number of optimal solutions. We will see how we can find an alternative optimal solutions as well as an infinite number of optimal solutions for an LPP by an example. We consider the example here as maximize z equal to 4x1 plus 14x2, and there are some constraints. There are two constraints which are all less than equal to type. Then we will first convert this problem into standard form to feed into the simplex table, and in the simplex table, as you can see in the first iteration, Z2 minus C2 is most negative. So, A2 is the entering vector and it has two positive components. So, from the minimum ratio we decide A3 as the departing vector. In the next iteration we find that Zj minus Cj is greater than equal to 0 for all j. Hence, the condition for optimality is satisfied. An optimal solution of the problem is thus obtained x1 equal to 0 and x2 equal to 3, and the corresponding value of the objective function can be obtained as 42. However, note that Zj minus Cj value corresponding to the non-basic variable x1 is 0. This indicates that there is an alternative optimal solution of the problem. Thus, by entering A1 into the basis, we can obtain another optimal solution as x1 equal to 7 by 3 and x2 equal to 7 by 3, and in that case the value of the objective function remain the same as 42.
Since we have two optimal solutions, x1 equal to 0 and x2 equal to 3 and x1 equal to x2 equal to 7 by 3, the problem has an infinite number of solutions which can be obtained as convex combination of these two solutions.
Let us now consider another special case, which is the case of unbounded solution in LPP. In general, an unbounded solution can be detected at any iteration if all the coefficients aij is less than equal to 0, I equal to 1 to up to m for the entering vector aj for which zj minus cj is less than 0. To consider this special case, we take an example which is shown in this slide. In the simplex table, we see that in the first iteration z1 minus c1 is most negative, so a1 is the entering vector, and clearly we can select a3 as the departing vector. Thus, the basis a3 a4 now change to a1 a4 in the second iteration. In the second iteration, we find that z2 minus c2 is the only negative, thus a2 will be the entering vector. But a2 has two components, one is 0 and another one is minus 1. That means that we are unable to select a key element. Thus, the problem has an unbounded solution. Next, we come to the special case of no feasible solution in LPP. If at any stage of simplex computation, one or more artificial variables appears in the basis at positive level, then the problem is said to have no feasible solutions. Let us consider an example which is shown in this slide. Maximize z equal to 2x1 plus x2 subject to two constants, one is greater than equal to and another is less than equal to type.
We first convert the problem in the standard form and put in simplex table. Here we introduce surplus variable x3, slack variable x4 and artificial variable x5 to convert the problem to standard form.
So, when this problem is fitted into the simplex table, we see that in the first iteration a2 is the entering vector and a4 is the departing vector.
While in the second iteration a5 and a2 form the basis, and we see that zj minus cj is greater than equal to 0 for all j.
That means optimality condition has been satisfied, but the artificial variable x5 appears in the basis at the positive level and it takes the value 1. Since the artificial variable appears in the basis at positive level, so this problem has no feasible solution. In this module, we have so far discussed some special cases in LPP. Cases like degeneracy in LPP, LPP with unrestricted variables. In case of degeneracy, one must be very careful to resolve the degeneracy, that is, to select the departing vector if there is a tie in the minimum ratio. Otherwise, the case of cycling may arrive, and if the case of cycling arrive, then one never gets the optimal solutions. One may think that if an LPP has a finite number of decision variable, then it has a finite number of basic feasible solutions. If there is finite number of basic feasible solutions, then one may expect to get the optimal solutions in a finite number of iterations. This may not happen if there is a degeneracy in the problem. Degeneracy will not allow you to reach to the optimal solution. That means the same basic feasible solution will repeat after some iterations so that the cycling process will go on. In case of LPP with unrestricted variables, there may be some applications. If we think of solving a system of linear equations, then such a technique can be applied. That means, if we want to solve a system equation by simplex method, the system of equations are given but the variables are not defined. That means, we have to consider the variables as unrestricted in signs, and in that case also we have to define a dummy objective functions and fit into the simplex table. Except these two cases, we have also considered some other special cases like LPP with no feasible solution, LPP with unbounded solution, or LPP with unbounded solutions. With this, we end this module.